I'm going to start a few minutes early. You may hear echoes, but that's audio. Okay, you test the audio. Let me take a few minute delay. All right, so what you see here is the chapter 14. I've decided to use this in a PDF book because I can, as you can see, I can write on the screen there. So, of course, this section is titled Kinetics of Particle Working Energy. So what I'm planning to do is go through the entire chapter, copying sections and giving you a perspective for the whole thing, and then giving you my perspective at the end. Okay, so he starts off with work of a force, and you've seen it before, F dot X, where these are both vectors, and you've got to move in that direction. So guess what? If you want to, here, let's do it just like the way he's doing it, so not being too much different. F dot ds, where those are two vectors, and essentially it becomes the magnitude of that, the magnitude of ds, and the cosine of the angle between them, because that's the definition of the dot product. Physics, this may be changed to an x. It doesn't matter what it is, or a delta. It could be anything. In this book, he's decided to use an S. So as you move through here, he also, obviously, he's come through here and he said the R is the displacement. So there's dr, there's your R, there's the R at the new time. I don't know what this repeated means unless this, yeah, it's the same picture as before. Then he goes through the work of a variable force. Now, a variable force might be a spring. So if you look at a spring and you initially push on a spring, and here's where your spring is, and you push on it with a force, if it's unsprung or unstretched, that's going to be your force value. As you push it deeper and deeper and deeper, it's harder to push it. Now, most of the time, springs are modeled like F is equal to Kx, where this is the X and this is the X. That's a common thing. Now, what do? Okay, yeah, first you take the dot product. You make sure your force is in the direction, that you're only accounting for the deflection in the direction of the force. And then what are you doing? Your ds sits right here, and here's your S. You can, and there are problems in this book where he wants you to deflect it from here to here. And essentially, it's the area in there. That's what he's doing right here. He's kind of showing that actually it doesn't matter whether it's linear or not. It's still the area under the diagram. That, in fact, is the energy taken to get from point 1 to point 2. So that's a common thing that he's talking about here, we'll list all this. That's the energy of some sort of force. Or, okay, let me take it back. He's using the term work of a variable force to go from state 1 to state 2. Nothing fancy. You have work of a constant force along a straight line. That's, guess what, the same thing. It's the area under that, but the equation becomes a lot easier in that this is a constant force. It does not have to be drawn in the integral, and you get this. Okay, now this is where work of a weight. Now, so this is going from place or state 1 to state 2. Notice he's saying the weight only goes down. In other words, we have a coordinate system that might look like this. X, well, you know, he's saying X, Y, and Z like this. Gravity acts in the negative J direction, so you got a minus sign, and there's your weight. You get down here and you move a certain distance in the Y, so state 1 might be up here, state 2 a little lower. So going from state 1 to state 2 is equal to this. Well, guess what? The weight is nothing more than mg, and as it turns out, he's saying delta y. So this is something you've seen before, mgh, in your equations in physics. And, oh, he had, okay, so I did all that diagram here, but I should have moved the page here a little bit because there's a picture of that. So here, work of a spring, we talked about that just a few seconds ago. You have an S in here. Because of that, you get a 1/2 K S squared evaluated from S1, S2. That's the integral of that thing. And you get the energy from 1 to 2 there. Okay, so here he's basically setting this up as the same thing. Occasionally I may here. Now, okay, so we've given you some problems here. Okay, so we're going to jump back to these, but I want to go over the whole thing here, and then we're going to go back and work some problems. So he talks about principles of work and energy. So you basically have an equation that, okay, so let's see. If I slide this to the left or the right, sorry. Okay, so I can just write over here. So F is equal to MA, right? Well, that's written as something that is publicly acceptable. But actually the equation is F is equal to this. And so you'll end up with an MV over here. So we'll come back to some of this in the next section, but for right now, I'm just going to toss it out and say, okay, if we stare at this equation and we end up looking at this work applied, and he has a sum out here because I guess you could have multiple, then you'll end up on this right hand side with 1/2 mv squared. So that's the kinetic energy. Now, yeah, that's true, but this is more written it's more written as kinetic energy from state 1 to state 2. Now notice what he does. Okay, so here's where I'm going to start grabbing a few equations and laying these out, and then lay out my approach to this whole thing. I have a more, I'm not saying my approach is any better than anybody else's, but mine goes a little bit more universal in what actually. So I'm going to go ahead and list this equation. I'm going to drop it in here. And then we're going to keep going. And so what happens, you move along through here. He has some problems to work. He talks about using this equation. And then a few seconds later, he'll have, principles of work of systems of particles. Okay? Now this is the fact that you might have 4 or 5 particles in there. All you have to do is add up the work and energy on all of them. Now he goes in here and he says, hey, wait a minute. It's possible that I have friction. Now here's the unique thing about friction. Friction is not a conservative force. So what happens as you move this, all you're doing is changing the temperature of this area right here by creating friction. So energy is taken away from that system. Before, it was looked at as if it was conservative. In other words, if I had a certain amount of energy in this block, and I moved it up, and then dropped it, when it got back down to here, I'd have the same energy. However, it depends on how I move this up. For example, give you a more concrete example. I have a block sliding on something that has no friction, and it rolls back up. Or say it's a wheel. So it goes this way. Say it's going 1 meter per second. It's losing no energy, no friction. As it goes down through here, it comes back up, and the wheel ends up back here. If it lost no energy, it's still going 1 meter per second. If it lost energy due to friction, it might not even make it up the hill. It might go to right here and lose the energy between them. So essentially, your energy state in the previous section said you weren't losing any energy to friction or anything. Now we're being introduced to this concept that, hey, wait a minute, I might lose energy along the way. And usually this is done, lost by some type of friction. We're specifically going to focus on the friction that sits right here. There are other types of friction, like fluid friction, which don't necessarily behave this way. But essentially, if you had a block sliding on a plane, you have a normal force. There's going to be your friction force as it's moving. And as it moves, this friction force times the distance it moves is going to be the work, or the energy, I'll just say E, lost. You've lost that energy. You're not getting that back. You're just heating up the bottom of the block here, and you're heating up the surface you're sliding on. That's all you're doing here. But it's not conservative. It cannot be harvested back. Just keep going down, and he comes up with problems. Now, we're not going to look at those until we assess the whole chapter. Keep going. Here's some more problems. Here's some more problems. Here's some more problems. And in the next section, here I'll slide on. We'll go back and work some of these and work the ones that are online. I've decided to use this textbook because I can move around, and like I said earlier, I can accentuate this thing. Let's see if I do that. I have to hit the delete. No. Okay, there's power. Okay, so if you have a force and it moves through a distance, it's going to be a foot pound. So if you have a foot-pound, that's fine. You know, that's a version of work. For example, if a person came, and I used to do this, to walk 9 floors every morning, but if I did it in a period of 30 minutes, I would not be as tired as if I used to do it in 10 minutes, because I'm expending more power to go up those stairs faster. So in fact, what you need is a delta T under there, which is that. And under that, you would have a new term, F dot velocity, which would be units of pounds feet per second. Now it turns out, he may have it down here. Yeah, he has it right here. So 1 horsepower is equal to 550 foot-pounds every second. Now the SI unit is a little bit more homogenized in the sense that 1 Newton meter per second is 1 joule per second, which is 1 watt. So they've made it so that these kind of line up, and you don't have to remember that 550 because they don't have that kind of stuff in SI. And that's one of the things about SI. Oh, okay. He says for conversion between the two systems, the horsepower is roughly, or I guess he's saying exactly equal to 745 watts. Now, your efficiency, if there's friction, for example, in a system, and legitimately there always is, then you're not gonna get out what you put in. You're gonna get out a little bit less. And so he has this symbol. It looks like an epsilon to me. That's the efficiency. Now he does come down here and say power, and comes down here and says that energy over energy. That's okay because it's the same time interval, and so you're getting away with that. That's okay. So now he's going to go in and say how much watts is this person putting out, things like that. I do not know how many problems are in this section. Okay. And now he goes into something called a section that's called conservative forces and potential energy. It's almost like a small repeat, okay, but there's new notation. And let me kind of go through this a little bit. He's got conservative force. He defines a conservative force. He shows on the right, a datum, which is you have to have in all these problems, and we'll show you that in a second. Talks about energy, then gravitational potential energy. That's nothing more than mg8, what you've seen before. And then you got a potential energy that's from the spring. And then you should go down. And he says, okay, you got a couple potential energies. I'll list them this way. This and this. And then I'll say U from 1 to 2 is the state at 1 minus the state at 2, if it's conservative. And then he goes through and starts solving problems. He comes back with this concept of, okay, well, he never really wrote out MGH, but this is what is implied. Now, here's the thing. Okay, he has new notation here. Now, a lot of people get hung up in these notations. And so I'll go over here and put them down right there. Now, what I'm going to tell you in a minute is, I just put it right there with it. A little smaller. It's okay. You go through all this, systems of particles. You could have the summed across several. You go through all these problems, and then what you'll find the end of the chapter coming up on you pretty close, pretty quick, and you find there's your end. So what have you done here? Okay, and how should you approach this? Okay. You could get hung up in the notation, which I've noticed some people do, and I think sometimes some people like to. The T's are the same. And so then the question becomes, what's this, and what's this, and what's this? So let me give you an alternate approach. And let me give you an alternate approach just based upon the fact that we come up with a problem. Let's say we come up with a problem. I have a block. I'm just going to make a problem up, say 1 kilogram, just because I can multiply that pretty easy. Smooth surface. Then it goes downhill. And then over a period here, say right here, it's a rough surface. And then go back to a smooth surface, go back up, and then you hit a spring. So the spring stiffness is K is equal to, 2 newtons per every meter that you squish it. We're going to say this little section is 25 meters long, and the mu here is going to be 0.1. It doesn't have a lot of friction, but it does have some friction. We're going to also say that this height is, this might not be the scale, is 100 meters, so it's pretty tall. And this height is 25 meters. So as you look at this problem, the inevitable question might come to you and says, okay, 1, what's the velocity just before, I'll call it A hits the spring? 2, what's the maximum deflection of the spring? Okay, so we'll look at both of those, and then in the light that says, okay, you got a lot here, just gonna leave that above the problem and say, there's my questions. So my question for this problem, or problem statement, is that now you can get hung up and start thinking about, okay, which one of these should I use? What should I do? I don't know what to do with this. Or you can simply come back to a simple approach like this. Okay, let me make sure my pen is a deep enough, let's do that, make it darker. Okay, so, okay, let's look at state 1. First, let's identify all the different types of energy that might be put in here. I've got a 1/2. I don't like that. Okay, I got a 1/2. I don't like that either. I got a 1/2 mv squared. Those are all the kinetic energies. And then I have 1/2 K times some type of deflection squared. That could be a potential energy somehow, if you have a spring, which you do. And then you got one or M, okay, let's make it MGH. That's a potential energy. And that's pretty much it, except I could have an F dot S, say, where these are two vectors. And this is, and actually if you look back, that this equation was how we derived that, and it's how we derived that. If you look back in the text, you'll find that. So this covers all others. So now what we need to do is we need to identify state 1 and state 2, because he did that too, state 1 and state 2. I'll say state 1 sits right back here. Now, I have one state 2 here, which is just before the spring. Okay. And I got another state here too, another one. So essentially what I'm saying is I have two different particular problems. This one and this one. So this state 2, I'll call it 2 prime, is when the spring is deflected the most at a maximum. Okay, when that's the case, that's what you got. So now, how do we do this? Well, let us list all the different energies that could exist in state 1. MGH1 plus 1/2 MV1 squared plus 1/2 KS1 squared. And that's it. So those are all the energies that could have existed in state 1. Now, you may ask the question, hey, wait a minute, why are you putting that in state 1? Well, let's say this spring is pre-compressed. It's already compressed. He'll show that in the book by showing a little cable attached here. So this is a cable here and here that's saying the spring is pre-compressed. Pre-compressed by 1 meter. That's quite a bit. But I don't have a high K there. Maybe I'll make it a little higher. 20 newtons per meter. So the spring is actually pre-compressed. Now, when you look at this, you're like, hey, wait a minute. You were talking about the state of energy of this mass. Why are you including that? And the thing is, this is at T1. This is essentially all entities at T1. So essentially, that spring is an entity here. That mass is an entity. They both have to be included here. So this is all entities at T1. Now, when you go from 1 to 2, what do you come across? You start off, and there's no friction, you're moving along. You go down, and bam, you hit this thing, and you get your energy scraped away. So we're going to have to deal with this part right here in a special way. Then you go back uphill, and then you hit that thing. So T2 is when that block sits right there. What did it do between 1 and 2? Well, it went across this. So if it goes across that, okay, then we have to have plus F dot, and I use the S, so I'm going to use that here. And I'm using that only because he's used that. This is what happens in essence. You could think of this as being that one. But you don't have to write it that way. You just have to identify what did this system experience. And here, let me finish this up by writing this. Now, this is a little interesting that I'm going to do. I'm just going to do a copy and then a paste. And then I'm going to put it over here. And doing this copy and pasting kind of accentuates the fact that I'm at T2. Here I'm at T1. This is what happened between T1 and T2. And what happened, I mean, it could be a variety of things. I only put one friction there, but you could have put 2 or 3. I could have put a block here that was friction here. I could have put this heel had some friction. I could have done several things like that. So I would have to include all of those. So let's take a look at this. Okay, so let's look at each of these terms. I'm going to start over here. And I'm going to start with the MGH. Well, my block is 1 kilogram. So MGH1 is going to be nothing more than 1 times the G is 9.81. The height. So I have to identify datum. Me, I always pick the lowest level. So I pick the lowest level. That gives me 100 to that upper. So that tells me that's 100. So plus 1/2 mv1 squared. So it's 1/2. It's still 1 kilogram. The velocity now. Well, first of all, the problem you got is if it's had no velocity, it's not going to move down here. So I need to put a velocity in here. So I'll say 5 meters per second. Look at this thing. So that's 5 meters per second. Now the next term, plus 1/2 K S1 squared. Now, it is true we have identified and been focusing back here, but now, at the same time, T1, that spring is still sitting there being compressed. And it's pre-compressed with a 1 meter, or plus 1/2. My K, I changed it to 20. And it's compressed, or pre-compressed by 1 meter. That's easy to do, squared. Now let's look at this term. So I've got this term, I got this now, F dot S. How do we do that? Well, here we kind of break it apart and do a free body diagram. So I'm going to copy this green stuff down here, and we're going to focus on it below this. So here's your friction platform, so to speak. Here's your block. As it goes across here, how far did it go? I'm going to zoom in on this in a second. It went 25 meters. So this, in fact, is, I'm going to do it down here, 25 meters. But as it's going, this block is sliding down here to the right. So its velocity is this direction. What is the force then? Oh, and it's 1 kilogram times 9.81 meters per second squared, or 9.81 newtons heavy. So that's the weight of it. So now the ground has to push back up the same value of 9.81 newtons, but the friction that gets pulled back, and maybe I should have done this a little bit more, a little higher value. F is equal to mu times normal, or 0.1 times 9.81. So that's not a lot of force there. But now let's look at it. Let's look at this term. It says F dot S. So the F is going to the left. The dot S, so S is going to the right. The force, friction, is going to the left. They're going in opposite directions. So if you have F, magnitude, and S, and cosine of the angle between the F and the S, you'll find is put S here, put F here. That's 180 degrees. If you look at cosine, here's your 180 degrees. And it's a -1. So you get a minus, and we'll talk about the implications of that minus. This minus is pretty important here. Minus, now the force isn't very much, 0.981, and I regret making the mu so small. I should have made it bigger, but it's too late now, and I'm not going to worry about it. The numbers are not going to be as important as the methodology. And the S it moved was 25 meters. But the minus, let's take a look at that for a minute. The minus means you take a block of energy, that's T1, you subtract some energy. The friction is taking away. Okay, and that is because it's taking away because the dot product is in the opposite direction. The dot product gives you a negative. So it takes away energy, and you end up with the energy at time 2. So the fact that that's a minus means you're taking energy away. When would you have a plus? Okay, let me give you an example. Just a simple example, a block. Somebody pushes the block with 100 pounds. The block itself is 100 pounds. The mu is equal, well, let me just say the mu is 0. Let's just say that for this particular case. So let's say, okay, so we'll just put up there, it's 100. Maybe I should change it to something besides 100. How about a 1 pound block? So a 1 pound block would be, I think that F is equal to MA, and 1 pound equal to so many slugs per 32.2 feet per second squared, means that mass is 1/32. So the mass of this thing is equal 1/32.2. That doesn't matter at this particular point. So this is a distraction right here. I didn't mean to distract you here. This is the important point. You're pushing this block along. It is moving this way. Say it moved 25 feet. Okay, so if I took F and dotted with S here, they are both going in the same direction. So I would have 100 pounds times 25, and the cosine of 0, the angle between this vector and that vector is 0, gives me a +1, meaning if I had this in an equation, I would have the energy at T1 plus adding some energy, in this case, 25 with 2 zeros, and that would equal to the energy at T2. So obviously, this energy is going to be higher than this energy. So E2, in this case, is going to be a little bit more than E1. Don't know exactly how much more. Well, I do know how much more, that much. So in fact, you can have energy added to the system if you are adding energy to the system. And the dot product is how the sign is constructed. So this dot product will tell you, whether or not you are taking energy away or whether you are adding. So now let's go back to our particular problem. In ours, we are taking away because of friction. Energy. Oh, shoot. Wrong button. Okay, you get back to my problem. Then my problem is that I slid along this surface. Here's what my situation was. I slid along this surface for 25 meters, and I scraped away just a tiny amount of energy. You'll find out when you really look at these terms that this value is pretty small. Now, in problems that he's constructing in the book, he'll try to make them so that that's not the case. In other words, if I would have made the mass a little different and different variables, different 100 meters smaller and things like that, I would have gotten that this energy is a little bit more significant. Okay, so the right hand side, MGH1. Okay, H, I move back up 25 feet. Remember, state T2 is when this block sits right here, just about to hit that thing. So it is flying to the right, and it's about to hit it. Okay, MGH2. M, I think it's still 1 kilogram. Still 1 kilogram, still 9.81. However, it went down the hill and back up to an elevation of 25. So it came back up to right there. Now, 1/2, and these don't have to be in any particular order. You know, this one could come second or third or whatever. It doesn't really matter. So 1/2, still 1 kilogram. This is the part I don't know. This is what I'm going to be searching for. The spring. What about the spring? Well, the spring in this particular state hasn't even been hit yet. So it's not compressed at all from the mass. It still has its pre-compressed state, which, believe it or not, is that same value. So it hasn't compressed at all. So I'm going to do a copy, and I'm going to just copy that thing and put it like right there. I think it goes, yeah, it goes to the bottom of this thing. Yeah. And so I'm just copying it. So what do you have? You have everything here. Now, the first thing you'll notice is this term right here is going to cancel that term because it's pre-compressed at the same level. You will know, let's see, something that's a little, yeah. You'll know this value. You can calculate that value. You can calculate that value. Move that value over to the left-hand side. And you can solve this for V2. Now, with that in mind, let's look at when the spring is deflected. This is awful handwriting. When the spring is deflected at the maximum. So now what I'm going to do is I'm going to take the same equation. I'm going to copy this whole equation. I'm going to put a blue mark around it and say, hey, this is the answer to 1. If you want to calculate it, you're free to calculate if you want to. We'll do a copy, and you'll see why I'm doing a copy in a minute. Put the thing right there. Okay, so this in fact is the answer. Here, put the escape key. This in fact is the answer to statement 1. Statement 1 being this statement. Now, what's the answer to statement 2 here? Statement 2 is what's the deflection of the spring? Okay, the initial energy over here remains the same. And the other thing is, it still passed through this part to compress this spring. So believe it or not, this one stays the same. Now, Okay, and I have a thing I should have corrected here. This should have said 2. Oops, okay. This should have said 2. Okay. This should have said, okay, wait a minute. Give me a second here. This should say 2, and this should say 1/2. In this particular case, KS2 squared. Okay, now state 2 primed is different than state 2. State 2 primed is the spring compressed. So it would be as if this block here, we're actually compress this spring back, and the spring, here's the block, and the spring is compressed back here. So it turns out, when is its maximum? Hang on. V2 primed would be 0 when it was a maximum. So it would be compressed to the point where the velocity would stop and it return. What would H2 prime be? Well, they're both at 25 meters, so that's the same energy state. What is the compression? I don't know. That's the key there. Let's see if I can get rid of that. Now I'm looking at S2 prime squared. This is the unknown now. Tells you how far you compress that spring. When it reached its maximum, the velocity was 0. This is still the same. So if you look at that whole problem, over on the left, the energy was the same. It was the same at T1. You still went through this region, and now your final state is different. So in fact, if you go through this, you can calculate it if you felt so inclined. You can actually go through and do this. Now, let me recap and say my approach to generally starting these problems. Okay, his approach is to look at these particular variables. If in fact you have a if in fact you have an unconservative mode or of energy, meaning friction or something like that, that term exists, right? But you have to think about this. So say, but this term has to have embedded in it that and this. This one is for purely conservative, meaning there's no friction or anything like that. The general form for me would be, well, think about it. From my perspective, I see here's the set of all problems that are unconservative, meaning they have friction or they have somebody pushing on something. These are all those type of problems. Inside that set might be ones that have no friction and nobody pushing. So if I was able to write an equation that covered all these by nature, it would cover all of it. So here's my approach. My approach is to identify all the different versions of energy. Okay, so I've got something that happens at T1. What are all the versions of energy? 1/2 mv squared, V1 squared, plus mgh1 plus 1/2 ks squared. These are all the states of energy that can occur there. Now, I can also have a bunch of different forces all against a bunch of different S's. In other words, say the block took off and it went across a sandpaper section, then a smooth section, then another sandpaper section, then a smooth, then another sandpaper. It would have 3 different of these terms. And so if you want, you could cover all that with just a blanket statement with a summation. You could also have a guy pushing this. So if somebody's pushing it to get it to go down the hill. Okay, when they're pushing it, they have to push it over a little rough section. Then they pushed it down the hill and they're done. So what did they do during this period? They put an F dot S in there. And since the direction it's moving and they're pushing it is the same, it would be a positive value, adding energy. But during this little part, you have another part of value, which has a little F going back the other way. And since it's moving to the right, you have a negative portion of energy. Say it gets down here, reaches these patches of sandpaper. That'll be a negative amount, taking out some energy. Another patch of sandpaper, taking out some energy. So you can see how this term right here covers all these type of situations. Situations where you're adding or taking away energy from the system. And then you identify, okay, at some time t2, you have 1/2 mv2 squared plus mgh2 plus 1/2 ks2 squared. And that I should have written with S1, so I apologize there. This is the energy state at T2. Now, this, you look back up there, this is sometimes what they call T. These could be massed together in what they might call V. But guess what? Some books actually call that a U. But it doesn't matter. To me, that's just a mnemonic identifying that that's kinetic energy and this is potential energy. That's fine. Do I need that symbol to solve these problems? No, I don't. So this mindset, moving across this state, helps in thermo as well. So, you can take energy in and out of the system. You can do whatever you want, but you're going to have an energy state at some particular point 1, energy state at some particular point 2, and that's just the way it's going to be. So the mindset in thermo is exactly the same way. You're going to have some energy at some particular time or state 1. Some stuff's going to happen. Maybe it's going to flow through something and gain some heat. Maybe it's going to flow through some sort of spinning paddle here, adding work to it. And it's going to come out and be over here at 2. Same concept. Maybe a few different terms because it's not going to necessarily be that term. But the same concept. When you add energy from 1 to 2, that means this energy at state 2 is slightly higher than energy at state 1. If you start taking energy out of it, say you have water up at some thing and you send it through a pipe and it goes through this turbine, comes out, and you run 2 wires back to your house and you get energy out of it. Well, energy, guess what? MGH is associated with the level of water. And then it comes out down here, and there's the MGH at the bottom. So guess what you find out? You have an energy at state 1. Somebody took some energy out to go to your house, E out to your house. How about that? And then you ended up with some energy down here. So, and that's energy 2. So energy 1 minus energy that got sucked out, went into your house, is equal to the energy at 2. So, in fact, that means energy 2 is going to be slightly less, hopefully a lot less, than energy at state 1. Same concept. So think of it like that. I mean, I know there's this concept with this V and U, things like that. Here, get this out here. But states, I like state 1. State 1 is everything in that at that time T1. State 2 is everything in there at T2. Now what you saw there was you saw I had a pre-compressed spring. So when I had that pre-compressed spring, I had to include that as energy back over here. The reason being is because it had energy with it. So the energy isn't always associated with this just one mass. Don't get that. I mean, that is associated with that one mass. But that spring has some energy pre-compressed into it. It's not associated with that mass at that time. So, so I think I'm going to be done. So that is the lump sum total of all of chapter 14, I think. Yeah, so that's conservation of energy. That's basically chapter 14 is just energy. And so what I'll do is come back and work some problems starting on Monday. Man, this thing. I think I brought it to its knees. Actually, I think you can touch it. Can you just touch it? There was a way. Oh, here's how you do it. You do like that. This is with all this stuff I've got going, it's really slowing down the computer. So this is a PDF. Just out of curiosity, this is something called, okay, you know, I forgot what that is. What is it called? Anyway, it's an app that I got off of PDF. No, I forgot. Here, if I do that, no. Anyway, I'll tell you on Monday what that is. We're done.